Hello, everyone. Thank you very much for joining us today. My name is Matthew, and I am one of the instructors, the teaching staff in the course. And Alexander is not with us immediately, but he does a lot of our behind-the-scenes work to help us get set up. I'm going to hand this over to Professor Impey, and we'll get started with questions.
Okay, welcome everyone. It's another hot day in the desert here. We had our hottest July on record, which means for 130 years or so last month and the month before, and last month was the hottest August on record. So we're kind of sweltering, but it's cool inside here where I'm answering your questions on astronomy, any subject. Go ahead.
All right, the very first question is from an email. Gabriela Santamaria sent an email saying, it is assumed that our galaxy and the Andromeda galaxy are going to collide and that the two black holes in the middle are going to cause an explosion. Do you think our planet would find another orbit?
The sort of answer to the final part of the question is yes, but probably not because of the black holes and what happens to them. So yes, the Andromeda galaxy and the Milky Way are almost certain to collide or meet and merge. The evidence for that has always been pretty good because we have an approach, as most galaxies are moving away from us due to the Hubble expansion. Andromeda is an exception. It's moving towards us at 100 kilometers per second. You can do the math, and given its distance, that projects to 3.5 to 4 billion years before it meets. Now, but it's possible that it's coming roughly towards us, but will sort of miss us. And that evidence got a little much better cinched up by the Hubble Space Telescope, which measured a transverse component of the motion over a long period of time with different images of the Andromeda Nebula, and has shown that really it is hitting almost exactly to us. So we will merge with Andromeda. The galaxies do have central black holes. Now, the galaxies will not make a direct head-to-head collision, nucleus to nucleus, so those black holes won't just hit each other. The galaxies will swirl around each other, and there'll be a slow settling of the galaxies into each other, merging with each other. And the black holes will do a slow spiral dance towards each other. Now, when they merge, they will, of course, double in size, minus a little bit, which is released in the form of gravitational waves. And so we'll end up with a 10 million solar mass black hole in the center of our galaxy by that time. But there's not an explosion associated with that. There's probably a release of energy because the black holes are accreting, and so they will be heating up material around them, but it's not an explosion that actually is going to disrupt the galaxies. Remember, the black holes at the center of galaxies mostly do not affect other than the very central region of the galaxies, and that's true when the galaxies merge as well. However, the interactions of the galaxies as they merge, because gravity has a long arm and decreases as the inverse square, then the orbits of stars throughout the galaxies will be affected, and there's roughly a coin toss chance, 1 in 2 chance, that at our distance from the center of the Milky Way, the sun and stars near it will be flung into a loose string of stars well above the galaxies and maybe out of them, maybe ejected out of them. So there's a possible chance the sun's situation will change dramatically when this merger happens. And remember, the merger does happen before the sun dies. So this is all during a period of time when there could be life on Earth, and other creatures may be watching this as it happens.
Excellent. Thank you very much. The next question is from Oliver Crosby, who's on with us live. Even though it's probably not very useful, have astronomers established any sort of universal north or up?
That's an interesting question. So the basic answer to the question is no, because the universe doesn't have a preferred direction. One of the premises of cosmology is what's called the cosmological principle, and that's that the universe is homogeneous and isotropic. The homogeneous part means that it's about the same at every location. So if we moved 1 billion light years away in any direction, we'd see galaxies and clusters and voids and superclusters the way we do in our region of the universe. The other part is the isotropy. That means it looks the same in any direction. And we've done this by measuring out in distance with deep surveys, and we don't see any difference to the distributions of galaxies, their Doppler shifts or expansion speeds, relative to the Milky Way. So there's no hint of a preferred direction to the universe from these surveys, and we've been doing them quite a long time. So in that sense, no, the universe has no orientation to speak of, and so it has no north or south or preferred cardinal points.
Excellent. Thank you very much. The next question is from one of our emails, and apparently there was a recent story about a black hole merger, and there were some surprising results. The masses were not what were expected. So can you talk a little bit about this black hole story? What happened, and why is it so unusual and exciting?
So this story has been lighting up the science headlines and the main newspapers, actually. The New York Times, it was a front page story a few days ago, is from the LIGO project, the Laser Interferometric Gravitational Observatory. Remember, LIGO is the project that first detected black hole mergers and gravitational waves in 2015, 2016, and Nobel Prize was awarded for that discovery just last year. So it's a very exciting project, and now LIGO is in routine operation. It's pretty much seeing a black hole merger or a neutron star black hole merger every few weeks. The one that was announced recently is very surprising. Most black holes should be somewhere above 3.5 times the mass of the sun, because black hole, that's the minimum mass of a black hole. Below that, a compact object would be a neutron star. Now, it's always been a little puzzling that the black hole mergers that have been seen in the first few years of LIGO all involve individual components that are well above that minimum mass. Most of them are 5 to 10, up to 20, or even 30 times the mass of the sun. So there's been a little surprise in the LIGO data right from the beginning, which is where are the low mass black holes that we would expect actually to see more of that are above the minimum mass. This new one was a surprise at the high end. So basically, the signal represented the merger of a 70 and an 80 solar mass black hole to form a 150 solar mass black hole. That's a huge black hole to be representative of the end of a star's life. Remember, at the center of galaxies, we have very massive black holes, but we're talking now about what happens after a star dies. So the black hole itself is the most massive black hole that's been seen in any of this data, 150 times the mass of the sun. But the problem is that the two pieces, the two smaller black holes that collided and merged to make the 150 solar mass black hole, they're too big to have naturally formed by star death. In other words, you take the most massive star we think can form a stable object, and when it dies, what is the most massive black hole you think you might get out of it? And the answer, depending on the models, is about 30 to 40 or maybe 50 times the mass of the sun. Nature should not make 60 or 70 solar mass black holes when a star dies. The reason is that if you had a sufficiently large and massive star that collapsed and started to form a stable star, it's unstable. It will not actually form a stable object, and it will not equally form a black hole. It'll just blow itself apart, leaving nothing behind. In other words, nature, as far as we know, no models and simulations, don't show any way to generate the dead star corpses that are that massive. So that's a pretty big problem. And the inference has been, there's no proof of this particularly, that the precursor to black holes, the 70 and the 80 solar mass black hole, were themselves the product of earlier mergers, perhaps a whole sequence of mergers going up from a few times the mass of the sun up to dozens of times the mass of the sun. Now, those mergers could have happened tens, hundreds, thousands of years ago, so there's no reason that LIGO would have seen these precursor mergers. But if this is the scenario, this is the only real scenario that makes any sense, and that implies that LIGO in this event is looking at a very dense region of stars and star corpses where the likelihood of black hole or star remnant collisions and mergers is very high. And so a sequence of black hole mergers led to the two large pieces that combined to make the thing that's now 150 times the mass of the sun. A pretty extraordinary story.
Excellent. Thank you very much. So Abhishek sent an email and would like to know if the age of the universe is 13.8 billion years, then why has it expanded to 93 billion light years in size now?
Right. That's a very good question, a natural question. The age is very well measured, by the Big Bang model, the expansion rate of the history of the universe, coupled with the amount of dark energy and dark matter it contains, give a pretty accurate age within a few percent, as well as we can measure these things that we don't completely understand. And that cross-checks against the age of the oldest stars in globular clusters. So we can trust the 13.8 billion years. It's not going to be wrong by very much. Now, the size of the observable universe, diameter, and 2 radii multiplied to get added together, is indeed 93 billion light years. And the reason it's more than twice 13.8 billion, which is what you would intuitively imagine, is because the universe for the first 5 or 6 billion years of its existence was expanding faster than light speed, which is to say any 2 points in space-time in the first third of the universe's history were moving apart faster than light speed, which actually means no information could be transmitted between those 2 points in space because they're moving apart faster than anything that can transmit information. The universe did slow down, was decelerating for the first part of its history, and so eventually those 2 points moving away faster than light speed could come into light communication. But because the early period of the history things were moving apart faster than light, then the diameter of the visible universe can be more than the diameter you would imagine by 13.8 billion years of light traveling. And that's the simple answer to the question. It's a factor of 3, essentially more. And that's because of the superluminal expansion of the entire universe early on.
Excellent. Thank you very much. The next question is from Hernan Reyes, who would like to know about Europa. And he would like to know, does the combination of the orbital resonance of the 3 Galilean moons and the gravitational pull of Jupiter generate sufficient tidal heating inside Europa's core for hydrothermal vents to exist on the floor of Europa? And can you talk about that and the possibility then for life existing on Europa and why that might be the case?
Right. So Europa is a very compelling target of interest for astrobiologists because it has oceans. It's watery, a more watery world than the Earth, in fact. The Earth is only 3/4 covered in water. Europa is entirely covered in water, and then on top of that, ice. We can't see through to the oceans, of course, and it's a very cold place, so that ice is extremely hard, granite hard. The question of what's the temperature of the water inside, especially at the base of those oceans, which are of unknown depth, but probably a few kilometers, maybe up to 5 or 10 kilometers deep, that's a matter of some debate. So the 2 heating sources available to Europa, given its large distance from the sun, 5 times the distance the Earth is, so the natural temperature there is very cold, well below the freezing point of water. The 2 extra heating sources are the tidal flexing of Europa, because it's in an elliptical orbit of Jupiter. So Jupiter, as a massive planet, is squeezing that moon, and that squeezing, it creates heat, just as if you squeezed a tennis ball or a squash ball or a racquetball, it would eventually get hot. Same mechanism. And the other source of heating, since it's a substantial sized moon, is radioactive heating from the natural rock material. That's the same radioactive heating that exists in the Earth and Mars and other large rocky objects. Now, planetary scientists don't completely agree on the relative components or the relative contributions of those 2 effects. They may be about equal, but actually some people think the tidal heating is twice as much as the rock heating from radioactive decay. Either way, they're both significant heat contributions to Europa, and they do indeed create the possibility that there is hydrothermal activity or hydrothermal vents at the base of the European Ocean that are heating the water not to anything like boiling point, but to, as in the Earth's oceans, hydrothermal activity creates superheated water. In Europa, that's unlikely. It would probably just create a tepid temperature, but that's interesting because microbial and biological activity keys to temperature. So any extra heat source is going to increase biological activity, the speed of reactions, the speed of a metabolism, if there is living organism there. And so it's very exciting for astrobiology. Unfortunately, resolving these issues of how much extra heat is there and is that enough heat to drive biology, and is there biology at all, that's going to take quite a while to answer because we're just doing remote sensing of Europa. The Europa Clipper mission, or its successors, because that mission has evolved in the last decade, will indeed visit Europa, and there'll be a very sophisticated orbiter, and potentially that orbiter will be splashing material off the ice by throwing a projectile at the ice and then sniffing what comes off to sample possible organic material in the ice. But there's no way at the moment to find a place where the ice crust is thin and either melt or drill through it and find out what's actually in the ocean. That's another whole mission away, which means it's decades away. But that is the long-term plan. We want to find that out.
Excellent. Thank you very much. We now have kind of several people have asked questions about the Higgs boson. Naroon Joe, who's on with us live, would just like you to talk about what it is, what are its properties, and what makes it special, and then we'll talk about the next one.
So the Higgs boson is a fundamental particle that's very important in high energy physics because it ties together what's called the standard model of particle physics. The standard model of particle physics describes heavy particles and light particles. The heavy particles are quarks, and there's 3 families of quarks, 6 different quarks. And the light particles, or leptons, are electron, muon, tau, and their partner neutrinos, another set of 3 families, 6 particles. So those 12 particles are key to the standard model. The question not answered by the standard model is, where do they get their mass from? Why are the masses of the different quarks different? Why are the masses of the electron, the muon, and the tau so different, and their respective neutrinos? Standard model doesn't tell you. And so the Higgs mechanism was proposed by Peter Higgs, physicist at the University of Edinburgh, now quite old but still active. And he won a Nobel Prize, of course, when the Higgs particle was discovered. He proposed a mechanism whereby mass would be ascribed to particles based on their interactions with something called the Higgs field. So his mechanism involves a field, like electromagnetic field, that permeates space. And essentially, if you like, the drag of a particle through this field based on its interaction with the field either creates a small amount of drag or viscous interaction, or a large amount. The small amount means a small mass, the large amount means a large mass. That's just a conceptual way of understanding it. And so the Higgs mechanism is a field permeating space that attributes mass to all particles. Still doesn't tell us why they have the very particular masses they do, but it explains where in principle mass comes from. Now the Higgs field has a carrier particle, or a particle that carries it through space or across space, and that's the Higgs boson. Boson means an integer spin particle, so photons are spin 0 and other particles have spin 1 or 2. These are integer spins. And so the boson of Higgs is similar to that. It's in the same category as a photon. And it was that particle that was detected with an energy of about 130 giga-electron volts by CERN, by the Large Hadron Collider, in 2012 and 2013. It took 2 seasons of data to finally find it. So it was a triumph, a great triumph of the standard model of particle physics, because the Higgs particle was predicted by Peter Higgs and a few other theorists in the 1960s, and it took almost half a century to actually detect. So it was a great success, but it doesn't answer all the issues of particle physics by any means.
Excellent. And then the next question that's related to that is from JKY Athavan, who would like to know, how is it that the collision of protons using the LHC can prove the existence of the Higgs boson? How were we able to find it, and what are we looking for?
Yeah, it's a good question, because it was a needle in a haystack. Most high-energy physics experiments now, like the ones at the Large Hadron Collider, are needle in a haystack experiments. So it's actually very crude. I mean, when you hurl particles at each other at very high speeds, close to the speed of light, you are essentially creating pure energy in the collision. And from that energy, you can create particles of particular masses. So the whole goal of the Large Hadron Collider was to hurl protons hard enough against each other that when they smashed apart and there were a lot of other interactions and other particles created, the energy was sufficient that a Higgs particle or boson could be created. In other words, you had to put enough energy in the collision that you had 130 giga-electron volts to play with at the other side. Now, when you have 130 gigaelectron volts of energy sitting in a tiny region of space, you can make all sorts of particles, many particles. You can make quarks, you can make electrons, you can make muons, you can make tau particles, you can make all sorts of particles, and they would all be made. So you have this horrible mess of particles coming out of a collision with that energy. And only a very small number, I think 3 pathways, involve an interaction with the Higgs boson. And it's an indirect interaction. It's not like Higgs particles are produced and they just fly off and you catch them in some other detector. You're actually looking for the Higgs effect by an intermediate stage that eventually leads to other particles that you then detect. So it's a little indirect, and you have to use inference, and you have to sift this very rare interaction from much more abundant interactions producing more mundane particles at lower and higher energies. And so that was a hard job, and they geared up for years to do it, and it took 2 seasons of data to be absolutely sure they'd detected the needle in the haystack. But they did. It was a triumph of experimental technique, actually, that the Higgs was detected the way it was and as quickly as it was.
Thank you. Lawrence, who's on with us live, would like to know, does our sun have a companion star? Is Proxima Centauri close enough to be considered a companion star? And if not, how close would one have to be?
No, it appears that our sun is an isolated star. It's unusual because more than half of all stars are either in binary or multiple groups or triple systems or whatever. So solo stars are the slight minority of all stars. The reason we know that our sun doesn't have a companion is that Proxima Centauri, we can measure the velocity, the space velocity of Proxima Centauri, its transverse and its radial velocity. And if we look at our sun's position in the Milky Way and the stars near it, and then Proxima Centauri shows no signs of being bound gravitationally to the sun, or have potentially been closer to the sun in orbit with it, and then having left the system or escaped somehow into more distant space. So the velocity and motion of Proxima Centauri is not consistent with it ever having been or being now a partner of the sun, and no star near the sun has that property. Now, there's a little wriggle room on that statement, because the sun was born 4.5 billion years ago, and the galaxy has been in an orbit of the galaxy almost 20 times since then, going in and out of the plane of the galaxy, and star groups migrating and merging and the environment changing. So it is actually possible that the star had not a close, tight companion, but a loose, gravitationally bound companion when it formed or soon after, that subsequent interactions or just slow migration caused to move away. So we can't rule that out, but we can say as we speak the sun does not have a companion.
All right, the next question is from Chandran, who's on with us live. Can a black hole merge with hundreds of other black holes and become a mega massive black hole and swallow the entire universe?
The answer to your question is yes, up until the last part, the swallow the universe part. It does appear that black holes merge sequentially to form bigger black holes. We saw an exotic example of this in the LIGO story of the formation of a 150 solar mass black hole, where the 2 pieces that went into that black hole were each too large to have resulted from a single star dying. And so it's almost certain that those 70 and 80 solar mass black holes were in turn produced by smaller black holes merging, and maybe smaller black holes before that. So this event where LIGO saw the creation of a 150 solar mass black hole was the result of a chain of black hole mergers. Not millions of black holes, but dozen maybe. So that's pretty exciting. Now, more generally, when you form massive black holes in the center of galaxies, those galaxies were built by mergers over time. So we think that the big galaxies in the universe, including the Milky Way, were formed by mergers and collisions of galaxies over 12 or 13 billion years. And in that time, hundreds of dwarf galaxies might combine to make one massive galaxy. And if those dwarf galaxies had black holes, those black holes would merge. So again, not millions of black holes, but now we're talking about possibly hundreds of individual black holes merging over time to produce a massive black hole in the center of our galaxy. So it is a lot of the job of astronomers to figure out this merger history, and LIGO is helping us detect the black hole merger part of that history. Now, those black holes, again, are confined to the centers of their galaxies. They don't really affect much more than the region nearly around them, and so they're not going to consume the galaxy they live in, let alone the entire universe. So we don't need to worry about a sort of catastrophic outcome of the formation of these black holes.
We have kind of follow-up to the question about life on Europa, and Hernan is on with us live. Hernan would like to know if we find life on Europa, what do you think the chances are that it will be independently evolved, and what are the what's the significance of such second genesis?
If life on Europa is found, it's hugely significant because it is a second genesis. It is life 2.0. And the reason we know that is that there is the transmission of material between objects in the solar system. So we have Martian meteorites on the Earth and lunar meteorites, so we know lunar and Martian material can reach us. And the conveyor belt tends to work more efficiently going towards the sun than away from the sun. But if you work out what are the odds that a terrestrial life-bearing rock could be blasted off the surface and then eventually reach Europa in the outer solar system, you can calculate those odds. If people have done this kind of calculation, it's incredibly small. I mean, the odds are essentially zero that a life-bearing Earth rock could reach Europa. In other words, if we see life on Europa, it didn't come from the Earth. It really did evolve independently. That same statement, of course, is not necessarily true of Mars, so that's an interesting distinction. So that's why, of course, biology on Europa would be extremely exciting, because it would be a separate data point in the abundance of life in the universe. And at the point at which you see two places with biology in one solar system, you've got to imagine that life in the universe is pretty widespread. When you only have one, and it's the Earth, and it's us, and we're unique, well, we might be unique. Now, the question of what is the likelihood that that biology, should it exist, is the same biology as terrestrial biology, that's, of course, a fascinating question. We'd love to know the answer. The chemistry of Europa and the oceans, it's very possibly it's definitely a saline ocean. We know that the ice has salt material in it. We don't quite know what the pH is, but the chemistry of the solar system is pretty uniform. So we know there are silicates and carbonates and heavy metals in roughly the same concentration. So the chemistry overall of Europa is not vastly different from the Earth. The physical conditions are different. And so would the biochemistry therefore be similar? Would the replicating molecule that holds information be similar? Would the cell and its structure be similar? We simply don't know, because that is a key question in astrobiology. If you had a similar set of starting conditions in terms of liquid water, local energy, and basic chemistry, do you always end up at the same point when biology starts? We'd love to know the answer to that question. And that's why looking for life on Europa eventually is one of the most important questions we can ask about the solar system.
Excellent, thank you. The next question is from Absek Ranjan, who's on with us live. Is the singularity within a black hole tied in any way with the origins of the Big Bang?
Not directly. The singularity that's implied to be at the center of every black hole, based on black hole theory, it represents a cusp of density. That is to say, a place where the mass density is infinite. And that's a non-physical situation. So the people who developed the black hole theory, including Stephen Hawking, who's well aware of this problem, have recognized that the singularity means black hole theory is incomplete, because we were not describing something well when we have an infinite cusp of mass at the center of a black hole. Now, the black holes that are based from dead stars or at the center of galaxies, they didn't exist when the universe started. They were formed by gravity acting on mass in the universe. So in that sense, the singularity nor the black holes themselves in the universe are not directly related to the Big Bang, because the Big Bang was a precursor event, after which there was a period of time when there were no black holes as the universe was expanding and cooling, and then later black holes formed. So in that sense, there's no direct connection.
Excellent. The next question is from Soham Das. We've talked before about um, avenues into astronomy as a profession from places like studying astronomy and also physics, but he would like to know, are there alternative routes? Could somebody come into it from mechanical engineering, for example?
Yes, it's possible. There are routes into it from aerospace and mechanical engineering. There are routes into astronomy from computer science because astronomy uses computational techniques a lot. Um, and so there are side routes into astronomy. I mean, and what it means is you could, using the core skill in another area like engineering or computer science, you could find yourself working on a major astronomical project. And in that project, there would be astronomers and engineers and data scientists and so on. And from a base in that project, you could clearly learn a lot from your colleagues. You could start studying online. You could boost your skills and put some courses under your belt. And so it is certainly possible to sort of migrate, if you like, into astronomy from a different field within the context of a large astronomy project, which is typically a big telescope or something like that.
Wolf and Bree, who's on with us live, would like to know if you could talk about what the Parker Solar Probe will be used for and what it's studying.
The Parker Solar Probe is the best solar observing facility we've had for decades. It's a NASA satellite, and it's named after Eugene Parker, who is a very famous physicist and astrophysicist at the University of Chicago. He lived till he was quite old. He's dead now. But he, in the 1950s and 60s, developed a foundational theory on how the sun works. He was working in magnetohydrodynamics, extremely difficult, complex field of mathematical physics, and he made great headway into understanding how the sun generates its magnetic field through the dynamo mechanism, why the sun's magnetic field eventually tangles and reverses, and so there's a solar cycle. So he produced a lot of foundational theory into our knowledge of how the sun works. But some questions were unanswered, even by him. And one of them is, why is the sun's corona so hot? So you go away from the photosphere of the sun at 5,700 Kelvin, and above the surface, the photosphere, and then the layer just above that is the corona, which is an outer layer that's extremely diffuse and laced with magnetic field and a temperature of 1 or 2 million Kelvin. And that's the corona that glows in X-rays. You can see X-ray pictures of the sun where the corona is booming in X-rays. It was very unclear to physicists for a long time why the surface of the sun at a temperature of under 6,000 Kelvin could somehow transmit enough energy to heat a layer above it to a temperature almost 100 times more, a few million Kelvin. And Eugene Parker had some ideas about this, about transmission of magnetic energy and acceleration of particles. But the solar probe that named after him, in large part, was designed to answer that question. It's the biggest missing piece of our knowledge of the sun, apart from the fact that the probe was beautifully equipped to observe the sun's activity in great detail and understand solar storms and prominences and the kind of eruption events that occur every decade or century that can really harm life on Earth and telecommunications for sure. So the solar probe is going to answer some profound questions about the sun, many of which were posed and understood by Eugene Parker himself.
Excellent. Thank you very much. The next question is from one of our live viewers as well. And Francine Kaplan would like to know, asteroids and meteors can crash into Earth and other planets. Is there any evidence that planets in other galaxies have collided with each other?
Not directly. So we've now got over 4,000, about 4,300, I think, is the current census, exoplanets, planets in other solar systems, and very many systems now. So at least 100 of these exoplanet systems have more than one planet detected. I think the biggest number is something like 8 or 9 in one system, as many as we have planets in our solar system. And we know what their orbits are and their masses, more or less. We haven't seen evidence of those planets colliding or combining. It's hard to measure the eccentricity of their orbits or the inclination of their orbits. That's the kind of detailed information you don't get from the method that detects them. So I'd say simply that the information we have of other solar systems is too primitive in terms of the orbits of those planets or how stable they are long term to make any judgment as to whether they've collided or combined. And in that case, all we have to go on is our knowledge of the solar system, and we know that the planets in our solar system in their current positions and orbits are long-term stable, which is to say for a few 100 million years at least, they're not going to change substantially.
All right, the next question is from one of our live viewers. What amount of radiation would a spaceship experience? The question asks when it goes beyond the Oort cloud, but can you talk about what kind of radiation we experience at various points in a trip through a solar system?
Well, you've got sort of two sources of radiation when you're traveling in the solar system. One is the radiation from the sun, and of course the two types of solar radiation that the atmosphere of the Earth protects us from are the ultraviolet radiation. That's what the ozone layer does. And then the high energy particles that come off the sun and the solar wind, they interact in our atmosphere. So in the solar system outside the Earth's orbit, you're subject to the UV radiation. Well, you can probably block that in a spaceship pretty well. And the cosmic rays or the high energy particles, not so much. They can be damaging. The other radiation that is out there is just ambient cosmic rays. So cosmic rays are high energy particles accelerated to really high energies and almost the speed of light, have origination elsewhere in the galaxy, caused in regions of star formation, or some of them even come from other galaxies, accelerated so much they travel through intergalactic space. So as you travel through the solar system, you'll be subject to these two types of ambient radiation. And they're high enough energy particles that they are damaging. They cause cellular damage. And they will pass through the thin skin of a spacecraft, some of them. Obviously, as you go further out from the sun, the solar radiation is less of a problem. So when you went to the Oort cloud and left the planet realm into the comet realm, the solar radiation is diminishing dramatically, so you don't need to worry about that. The cosmic rays, however, from other parts of the galaxy or even other galaxies, is the same. And so you'd have a cumulative exposure to that. And that probably, in the end, for a very long-term traveling in the solar system, is going to be a significant danger.
Thank you. The next question is from Akib, who's on with us live. Can you please share your thoughts on the Trappist system, which is 40 light years away, and the Teegarden system, 12 light years away? Both planets have habitable zones, planets in the habitable zones. Is there an update on these systems, or maybe you can provide some insight on other discoveries that might have planets in habitable zones?
Yeah, the Trappist, the Teegarden system is important and interesting, and the Trappist system is the best, actually, because it has at least 3 planets that are roughly Earth mass or size in the habitable zone of their star. They're much dimmer than the Sun's star. So that's pretty impressive. There's a 4th planet that's on the edge of the habitable zone, so it's possibly 4 habitable planets in one solar system compared to our solar system, which has 1. So these are good examples, and we hope through poring over Kepler data and satellites since then, to find more examples of multiple habitable planets in one system. To go beyond that, though, we have to understand what habitable means, or what is habitable actually inhabited, because you have to know something about the surface conditions of the planet and its atmosphere to really say whether potentially habitable means actually habitable. If, for example, a planet had a large and shrouding greenhouse gas atmosphere, it might actually be so hot that it's not habitable. On the other hand, if, like Mars, it has a very thin atmosphere for its distance from its star, it might have radiated so much heat into space that it's not habitable because it's too cold. So the habitability criterion is really based on the amount of radiation at that distance from its star, whether on the surface of a planet water would be in the liquid range. But whether it's actually liquid depends on the nature of the planet and its atmosphere. So that's the next step in all this work, is to try and diagnose the atmospheres of these Earth-like planets. In the Trappist system, for example, would be very exciting. And people have plans to do that. It's probably going to take a decade.
All right, the next question is from Scott Childs, who would like to know, does the LHC, the Large Hadron Collider, have any effect on Earth's magnetic field when it is running or tested?
That's an interesting question. No, it's the Large Hadron Collider does what it does through the use of superconducting magnets, because the protons that it's accelerating to very high energies, of course, positively charged, and they need to have a force exerted on them for them to stay in a circular orbit, because otherwise they, like Newton said, travel in straight lines undisturbed. So the LHC has extremely powerful and extremely precise magnets in a very particular configuration so as to keep the particles moving in their circular trajectory. The magnets there, the magnet strength where the particles are spinning around, is millions of times stronger than the Earth's magnetic field. So this instrument and these magnets don't see the Earth's magnetic field at all. It's negligible compared to them. And of course, these magnets themselves don't affect the Earth's magnetic field, because that much weaker magnetic field is permeating a planet that's thousands of times bigger than the LHC. So there's no real effect on the magnetic fields in either direction.
The next question is from Keith Crum, who would like to know, what is the next question or problem we need to solve that could lead us to interstellar travel?
We need a different mode of energy for accelerating a spacecraft. Everything so far has been, in the whole history of the space program, is based on chemical energy. And as impressive as Blue Origin's and SpaceX's achievements are in lowering the cost to orbit of a kilogram of payload by a factor of 10, or an order of magnitude in the last decade, that's really impressive work for two companies to do that, and they have the prospect of more. They're just squeezing efficiencies out of a kind of an obsolete technology, because it's the way we've got rockets into space since Apollo. So to go beyond that, to travel in the solar system, we need a different form of energy. Obviously, the most efficient energy that we know how to harness, because we do it at least in nuclear reactors for power, is fission power, nuclear fission. Harnessing that in a spaceship is challenging, because fission reactors are extremely massive amounts of metal and pipes and hydraulics and containment systems and heavy water to damp out radiation. You cannot replicate anything like even a miniaturized nuclear reactor in orbit and get it to generate a sufficient amount of speed. Now, we use nuclear decay, radioactive decay, to power spacecraft in the solar system, but those are just powering modest amounts of energy, typically hundreds of watts actually. To get a spacecraft moving fast, you need megawatts of energy somehow coming from a nuclear source. So we've got a lot of work to do. We've got to prototype technologies, and probably we'd want to go straight to a fusion model rather than a fission model, because that's more efficient fundamentally. But we obviously can't make fusion reactors work on the Earth for energy, so making them work in space is a step beyond what we can even do on the Earth. So most people think these methods are decades away, possibly 50, 60, maybe even 100 years. There are other methods with electromagnetic acceleration of particles and using plasmas to accelerate a spacecraft, and they're clever. And if you have a large scoop, you can harvest hydrogen from the interstellar medium or the interplanetary medium and use it as fuel for your nuclear reactor. So there are various technologies to go along with reactor technologies that would help us travel in space, but we just haven't done any engineering experiments off Earth, so we're a long way from it.
The next question is from Sudhanva, who is on with us live, who would like to know, sir, how does a black hole die? Or does it?
They don't die very easily or readily. According to Stephen Hawking and his theory, the black hole eventually evaporates. So Hawking radiation reflects the fact that in Hawking's theories of black holes have a very low temperature. For a solar mass black hole, it's about 1/1000th of a Kelvin, incredibly low temperature. But E equals mc squared, so the loss of energy is equivalent to the loss of mass, and so corresponding to the Hawking radiation is a slow evaporation of black holes. So that's a prediction of his theory, but the rate of that evaporation, just like the rate of that, the temperature of that radiation, is incredibly low. It's undetectably small, and so no one's been able to detect it, and I haven't really even tried because it's so far beyond what we could measure in space. So black holes are not eternal as far as the theory goes, but it's an untested theory, and that's important to remember.
The next question is from Valia, who is on with us live. Is it possible for a solar system to exist outside of a galaxy?
Yes, it is. It seems like we've found mechanisms, normal mechanisms, where in certain stellar configurations, remember a lot of stars are in binary or multiple systems, so you can transfer energy and angular momentum between stars in a bound system such that one member of the system gets a kick or gets a particular large amount of energy or angular momentum or both, enough to eject it from the system. And we've already seen particular examples where in the Milky Way we found single stars moving so fast that they are not bound to the galaxy. So we've seen, now we wouldn't detect those individual stars if they were far from the galaxy in intergalactic space, they'd just be too faint to see. But we've seen galaxies that are moving fast in the halo of our galaxy and are not bound to the galaxy. So these interactions they suffered have given one of the stars enough of a kick to let it escape the galaxy. So we know these mechanisms exist, and we've seen stars that, given sufficient time, will leave the galaxy and be floating through interstellar space. And since these stars, if they have planets, the planets will be in bound orbits of the stars. The stars themselves are getting a kick from a distance, not from up close. So the kick, it's not a physical kick, of course, it's a gravitational kick, would be unlikely to remove or strip the planets from the star. So yes, entire solar systems could be moving through intergalactic space. It's quite likely.
Excellent. Thank you very much. Next question is from Mayful Vaz Manzoor, who would like to know, what is the chance for any particular star that we see in the night sky to be dead or to have died, and how likely is it for the sky to be without stars someday?
So that's an interesting question associated with the fact that we see stars as they were, not as they are. So however far away a star is in light years is how old the light is we see it from. So to the first part of the question, is it possible that any of the stars we can see in the night sky, say with our eyes, are dead now? That would depend on us seeing a star that was far enough away, and the furthest stars you can see with your eye are maybe a few thousand light years, up to 10,000 light years, to have found a star that was late in its life where it happens to have died recently and that light of its death hasn't yet reached us. Now it turns out that most of the brightest stars and the ones that are furthest away from us in the sky, some of them are old, but many of them are actually young hot stars, so they're nowhere near dying. And of all the stars we can see in the sky, I don't think any of them are in the category where they're so near the end of their life, as far as we can measure it, that they may already have died, even though they were seeing their light. So it's an interesting question, but I think the answer is no. More generally, yes, the stars in the sky will all die. So as we move around the Milky Way, the stars that are in our part of the galaxy, that are visible to us in the night sky, they will change over time. Stars have motions, they have three-dimensional space motions, and if they're not bound to the nearby part of our galaxy, they will drift away and eventually be invisible, not in our night sky. So the night sky stars will change over time, over the next hundreds or billions of years. Some stars will come close, some stars will go far, young stars, old stars, but all of these stars will eventually die. So if you run the clock forward on the galaxy, and now you have to run it forward billions of years, eventually all the stars in our sky, whatever our sky looks like then, a different set of objects than the ones we see now, yes, they will all have died. They will become white dwarfs, cooling embers, or neutron stars or black holes. And so that's pretty much an inevitability of stellar evolution. And there won't be enough new stars to replace them because the gas that's left after stars die is slowly being mopped up into new stars and then trapped in stellar corpses. So eventually, and this is hundreds of billions of years now, there are no new stars to replace the old ones that have died. So indeed, our night sky will eventually, and that's a very long eventually, go black.
The next question is from El Ghazi, who's on with us live. Can you tell us what a cold plasma is?
So a cold plasma is, so plasma formally is a state of matter. It's, for physicists, it's distinct between solid, liquid, and gas. A plasma is more like a gas because it tends to be a low density substance where the energy is such that the electrons have all been stripped from the nuclei. And so it has sufficient temperature that the positively charged nuclei and the negatively charged electrons are free flowing through each other and around each other. So the plasmas tend to be hot, tens of thousands of kelvins up to hundreds of thousands or millions of kelvins. So these are very hot gases to make a plasma. So a cold plasma logically is a material where the electrons are not attached to the protons, but the temperature is actually low enough that they should be attached. And that essentially means a temperature lower than 3000 Kelvin basically, because then atoms would recombine, electrons would attach to protons, you'd have neutral hydrogen. And the only way you can arrange a cold plasma is in the laboratory, where you are able to still the motions of the charged particles by essentially electrical means and slow them down enough that under normal circumstances they would detach to each other and it would be a neutral gas. But in this case, you've kept them apart, so formally it's still a plasma, but it's a cold plasma because you've slowed them down.
The next question is sort of a follow-up from an earlier one. When a black hole dies, what's left over at the end? Is it going to be nothing, or will it be like a white dwarf floating in space? What remnant could be left over?
The black hole is the end point, and a white dwarf or neutron stars are different endpoints for different mass stars. So white dwarfs and neutron stars don't turn into anything else. They don't become black holes because they're not massive enough, basically. Neutron stars don't do anything. They just stay as pure neutron material, like a giant atomic nucleus. White dwarfs have a temperature, and so they're slowly radiating their residual heat into space and cooling forever. Black holes, according to the Hawking theory, are gradually evaporating and losing energy by their radiation. And what's left behind when that process is over is nothing. So basically the material, the mass that went into the black hole that sits within the event horizon is gradually being evaporated or sent off back into space, leaving nothing behind. That's what the theory says.
Excellent. Thank you very much. The next question is about the number of dimensions of the universe. So first of all, somebody has heard that we live in a two-dimensional version of a 3D universe or something like that. Can you talk about what dimensions are and the difference between the dimensions of space and of time?
So the conventional cosmology of the Big Bang, working with the theory of relativity, general relativity, is of a four-dimensional, and it's called a manifold in mathematical physics. Manifold just means a curved surface, a generalized surface. But you can call it a space if you want. So a four-dimensional space-time, 3 dimensions of space, 1 dimension of time. And they're connected. The space-time is hyphenated because general relativity couples space and time, their behaviors, the way they deviate from Newton's theory, and so on. So that's the conventional cosmology, 3-dimensional space and 1 dimension of time coupled to each other. Now more advanced theories that try to explain the unification of all the forces have been posited in terms of multidimensional spacetimes beyond the 4 that we see. The most elegant mathematical theories that are used for string theory calculation to explain the fundamental nature of matter, they tend to involve either 10 or 11 dimensions of space. And so in these spacetimes, you have to explain, therefore, why, if there are fundamentally 10 or 11 dimensions of space-time, why do we only see 3? What happens to the other 6 or 7 dimensions? And the answer in the theory is that those dimensions exist, but they only manifest at an extraordinarily high temperature or an extraordinarily small spatial scale, corresponding to the size of strings. And so these theories that are being used to describe the universe are based on unseen dimensions. And the question is, if the theories are so great, if they are so useful in mathematical terms to explain masses and particles, what would it take to see them, to say that the universe really is fundamentally 10-dimensional, 11-dimensional? And that is the point where everything gets hard, because testing these theories involves the creation of phenomenal energies unavailable to us in any accelerator, or accessing incredibly small scales, as small compared to an atom as an atom is compared to the Earth, for example. And that is also not easy to do. The only little sliver of hope involves the fact that some of these multidimensional space-time theories have mechanisms that affect the way gravity propagates that might manifest on intermediate scales, like a lab physics scale of meters. And so there are some lab physics experiments trying to look at whether space-time has more than 3 dimensions of space and 1 of time. None has succeeded so far, and I'd say they're probably not sensitive enough to succeed at all, but that's what people are looking for.
The next question is about stars, and the question is, why is it that iron is the heaviest element that can be created inside of the core of a star?
It's because iron is the most stable element in terms of its nuclear properties. So there's a fundamental diagram in physics which is called the binding energy graph, and it represents the binding energy per nucleon or per neutron or proton of different elements through the periodic table. And in this binding energy curve, this graph of the different elements, the minimum binding energy, and therefore the most stable nucleus, is iron. That's a minimum in the binding energy per nucleon compared to all other elements. And that means that as you move towards iron, by fusing nuclei together, you can get some energy out, get a little mass energy out, and that gives you free energy. That's how the sun makes its power, by fusion of hydrogen to helium. So that process works all the way up to iron. If you can force fusion to occur by creating a high enough temperature, you'll get a little net mass energy out, and so power or sunlight. But after that, iron is the most stable element, and so you no longer get a little mass energy benefit out of fusion, and so fusion will not naturally occur, and that means it's a dead end in star evolution. So you can get to iron, but you won't go any further. Doesn't matter, you can't make enough energy. The star is not hot enough for anything else to happen, and so it just stops there. It stalls out. To make you go beyond iron, some extra injection of energy is required, and in nature that happens in a supernova, or sometimes in the envelope of a giant star, or when neutron stars collide, for example, a cataclysmic event. When you get that extra injection of energy, then you can go beyond the stablest element, iron, to create the heavier elements.
Excellent, thank you very much. And this will be our last question. We are out of time for today, but we seem to get one of these fairly often. So can you talk about white holes? What are they, and could that be the origin of the universe, something like a white hole?
Well, the origin of the universe, it's an interesting question, because the universe did lead to an enormous net injection of energy, mass energy. Obviously, it was the creation of all matter, enough to create 100 billion galaxies, and enough energy to result in the expanding universe that subsequently is accelerating. So an enormous amount of energy injected and an enormous amount of mass created. In that sense, you might call the Big Bang a white hole, in a metaphorical sense. But white hole is not a formal physics term, because we don't have a physics object or a mechanism in physics that explains something called a white hole, as we do, for example, a black hole. That's a well understood physics term. Relates to gravity theory. It relates to the properties of a collapsed piece of space-time. So white holes are not equivalently well defined in physics, and so they're hypothetical. And as points out of space-time from which energy emerges, we have not seen evidence of that anywhere in space, anywhere in all the galaxies we've studied, whereas we have seen black holes. So we know they exist scattered through our galaxy, in other galaxies, in the centers of big galaxies everywhere in the universe. So the evidence for white holes, or something that you might describe as a white hole, is pretty thin. Basically, it's not there. We've not seen anything that we need that hypothesis to explain. And since white holes are not a natural prediction of stellar evolution or of the way the universe changes over time, that means they simply might not exist. And so I think at this point they're just a curiosity of theoretical physics. That's great to finish with, and thanks for your questions. As always, good questions, and we'll be back. We'll announce our next 2 sessions soon, and we'll be back with you pretty much every week. Okay, goodbye. And thanks to Matthew for facilitating, and invisible hand behind the scenes of Alexander as well.